I'm Holger Haas. I'm a staff research scientist here at IBM Quantum. Today, I'd like to give you a little bit of a walkthrough of what has been our trajectory here for building quantum computing hardware. And with an eye to the future, I want to lay out for you what we're currently working on and why we're so excited about it. The outline of my presentation is as follows. First, I'll start off with a brief intro to quantum information carriers, or qubits, and specifically the kind of qubits that we use here at IBM Quantum. I'll give you a 2-slide introduction to circuit quantum electrodynamics to bring us all to the same page. And then I'll flash you a photograph of what our quantum systems looked like 10 years ago. This will set the scene for understanding how far we've come in progressing with a variety of engineering challenges that building an error-correcting quantum computer requires us to do. And we'll look at various examples of these engineering challenges that we've tackled, specifically control electronics, wiring, packaging, gate errors and chip performance outside of gate errors. Then I'll turn my focus to the future and touch very briefly on the error-correcting codes that we intend to implement with our future hardware and lay out our plan for it. As you might already know, the distinction between classical and quantum computation lies in the fact that for encoding and processing classical information, you need an information carrier with a binary state. For example, voltage that you threshold to arrive at a binary variable with 0 and 1 state will suffice. And that is essentially what is used in classical computers. For quantum computation, however, you need an information carriers that can encode any state in the Hilbert space. In this slide, this any state is represented by these two complex numbers, alpha and beta. But of course, you need a little bit more than that for the quantum computer to be useful. What you need is you need to be able to encode multi-qubit states and perform arbitrary operations on it, usually in the form of a universal gate set. And you also need that information to survive sufficiently long that you can perform these operations. Usually we say that the quantum state needs to remain coherent. Finally, we need quantum information to be accessible. We need a means for reading out the qubit state, and that has to be efficient. So all this starts to sound like a bit of a shopping list. In the literature, these are what are called DiVincenzo criteria. At IBM Quantum, we build quantum computers using superconducting electrical circuits. And specifically, the circuit element that we use as a qubit is called a fixed frequency transmon qubit. However, before I tell you about that specific qubit, I want to first motivate why would we even turn to superconducting circuits. As I mentioned in the last slide, a key requirement for building a quantum computer is the survival of the quantum information, which essentially translates into wanting as little loss or dissipation in your hardware as possible. From that perspective, superconductors have that really desirable property. They come with no resistance or no dissipation. Now, of course, that doesn't actually mean that you have no loss. In fact, there are other types of loss, but it is a great start. Secondly, the second nice property of superconducting circuits is that they're electrical circuits. So that means that you can engineer them, you can design them just like any other electrical circuits. You can use the same tooling, both for design and manufacturing. This is highly desirable, and you can extend these circuits. You can add these extra qubits to your hardware, and you have the scalability component satisfied. Third, and very importantly, quite like with implementing classical logic, you need a nonlinear element. In the case of classical logic, this comes in the form of transistors. Here, superconducting circuits provide you a native element called the Josephson junction, which circuits make use of everywhere. This lies at the heart of our qubits. Finally, we have to acknowledge there is a price to pay. None of this comes for free, and for being able to build and control these superconducting circuits, we have to operate at millikelvin temperatures. However, most quantum computing platforms do need some kind of cooling anyway. At IBM Quantum, we build and operate qubits called the transmon qubit. The transmon was first proposed in the reference that we give here in the slide nearly 20 years ago. What it consists of is two elements. A Josephson junction, which in the circuit that you see there on the right-hand side is given by that box that has the cross inside, and a capacitor. If you actually look at one of our devices here on the left, you see that we engineer a capacitor by fabricating two paddles. The size of these paddles is order 100 micrometers in length. You see one there in that magnifying glass. In between these paddles, we fabricate the Josephson junction structure, which is much, much smaller in size. It's only about 100 times hundreds of nanometers big. And I give here the image of that in the middle of this slide. You see these tapered leads that come together. Both of these leads lead to either one of the capacitor plates, and where they come together, there's a very, very thin non-conducting barrier about 1 nanometer thick that's in between them, and that forms the Josephson junction. Now, what you can do is you can work yourself through these equations that are on this page, and you can show that effectively this object behaves as a nonlinear inductor. Now, why do we go through all this bother? The reason is that when you build such structure, then what ends up happening is that it behaves as a nonlinear oscillator. And the nonlinearity manifests itself in the fact that the energy levels of that oscillator have uneven spacings. So the energy level between 0 and 1 is different from the energy level from 1 to 2, and so on and so forth. So when we want to address it with microwaves, for example, we can isolate the 0 to 1 transition, and we won't hit the 1 to 2 transition as we drive the 0 to 1 transition. And that's critical for being able to build a quantum computer. Finally, it turns out that transmon has also some nice noise resilience properties that were deduced in that paper, also cited here. It is exponentially insensitive to electrical charge noise fluctuations in the environment, which leads to long coherence times. That's why we love it. Coherence time, as I said, is jargon for the survival time of the quantum state. Now, if we want to calculate the frequency of the transmon, then what we need to do is consider the elements that go into that transmon. Now, you see from the circuit diagram, there's only two elements really in it. There's the capacitor and the nonlinear inductor. So as you might guess, what you need is to know the capacitance, and for the inductor, you need to know the critical current of the Josephson junction. And from that, you can back out the energy or equivalently the frequency of the transmon. So there are other things that we can build with superconducting elements. For example, we can build resonators. On the right here, you can see a resonant circuit that consists of a linear inductor now and a capacitor instead of a nonlinear inductor. Equivalently, you could also consider a single mode in a transmission line that would also give you a resonant structure. For example, in this magnifying glass, you see a coplanar waveguide, and a single mode of that, maybe the lowest harmonic, would give you a resonant structure like that LC oscillator here. Now, the distinction between that and the transmon qubit is that here all the energy levels have an equal spacing. When you drive one of them, you drive all levels with the same frequency omega. What you can do with resonators is, for example, you can couple them to your transmon qubit. You can put a capacitor between this resonator and the transmon, and putting a capacitor between the transmon and the resonator could be as easy as just leaving a gap between them. And what you'll find is that if you get this right, and in certain regime, for example, in the regime of far detuned resonance mode, where the resonator could be at 7 gigahertz and your transmon at 5 gigahertz, then the frequency of the resonator becomes very weakly dependent on the transmon state. And what that is useful for is you can use this to detect the qubit state of the transmon. And this is exactly how we do it. Moreover, what the resonator is also useful for is for preventing the transmon from decaying, because if you make it off resonant, then at 7 gigahertz, it cannot accept the 5 gigahertz photon from the transmon. The math just doesn't work out. So now you have protected, we call it Purcell protection, the transmon from emitting a photon into the cavity. Finally, we can use this resonator for driving single qubit gates of the transmon. Here, we would need to use higher powers because we would drive them resonantly with the transmon, so at 5 gigahertz instead of 7 gigahertz for the resonator. But that's in some sense good, because that means that the distortions that the waveform experiences moving through that resonance structure at higher frequency are kept minimal. Now, one last thing to note about this magnifying glass image here on the left is that the resonator here on the left is actually not a readout resonator at all. That is a coupling resonator, but it's kind of hard to tell that because from the looks of it, they look pretty similar, but you have to trace them. And here you see that this one is connecting one qubit to another. That means it's a coupling resonator, but the resonator that connects a qubit to one of these triangular shapes on the edge of the chip would be a readout resonator, because that would connect the qubit to the outside world. Now, moving onwards, we start looking at the first experiment that one could really consider. And already here, with just applying 2 gates and a measurement, we start seeing some little bit of complexity that happens when we run an experiment on a quantum computer. What we do here in this circuit diagram, we apply a Hadamard gate and a Y gate on a qubit, and after that we apply a measurement. What actually happens when you press Shift Enter in your Jupyter notebook to run this circuit is, after you waited in a queue for this to be executed, then this circuit gets loaded onto the control hardware, and the control hardware will emit microwave pulses that get sent to the chip that's in the dilution fridge. And these control pulses, first for the gates, for that Hadamard and Y gate, travel down the cabling all the way to the chip from room temperature to millikelvin temperature stage and excite the qubit. And after applying the gates, we send in a pulse at a different frequency, resonant with the readout cavity, which is at frequency omega, and record back the signal that comes from the fridge to measure the qubit state. So having given you a little bit of a flavor of what happens when we do an experiment, I now want to show you how we used to run these things roughly about 10 years ago. So here what you see is a setup that we would have had in the lab 10 years ago. On the left, there is a full rack, roughly the size of a household fridge or so, full of microwave electronics. And this would have controlled order 10 qubits or so. In the middle, what you see is a dilution fridge. And the dilution fridge has these various circular plates. These are stages. And when we operate the fridge, then the fridge is closed. You can't see inside there. And it's all evacuated. So then these various circular stages are thermally isolated from one another. And that means we can keep them at different temperatures. And the way the fridge is built is that the warmest stages are at the top, and the coldest stage is the one that's the most bottom stage here. And that one is at about 20 millik above the absolute zero, or 0.02 Kelvin. That is where we mount our quantum chip. But to even mount a quantum chip there, we need a way of getting the signals that I just talked to you about, the control signals and the measurement signals, in and out of the chip. So we need some way of routing the signals onto the chip. And that means we need connectors, we need cables. So you can see that inside this fridge, there are these coaxial cables that run vertically that carry all of these signals, and the chip itself is mounted onto this printed circuit board or PCB, the bottom side of which has about 10 connectors that the coaxial cables would have mounted onto. And only on the right, there's this about a quarter-sized chip that has about 10 qubits on it. So all this infrastructure is necessary to control about 10 qubits. Now, if you stare at this image for a little while, you start realizing that having qubits and having that chip there on the right is not all that you need. You need more than that to build a quantum computer. You need packaging, you need cabling, you need room temperature electronics, all of which to support scaling this effort up to numbers that can support error correction or even utility scale workloads. And these pose engineering challenges, exactly the kinds of which we've been tackling for the past 10 years and we continue to tackle. So now I will tell you what has changed, what has been the progress that we've made over the past 10 years. So first, I'll walk you through how has our control electronics evolved over these 10 years. So bottom left is an electronics rack with commercial off-the-shelf electronics, and it's a full rack, like I said, about the size of a household fridge, and this could control and read out about 5 qubits or so. As you can imagine, if you want to do hundreds, thousands of qubits, this would fill up an enormous amount of space, and it would also cost a lot of money. Now, what we've been doing, we've been developing hardware for minimizing the footprint as well as cost, the control electronics. And we've been going generation after generation from 20 qubits to 40 qubits to 400 qubits in a single rack in our most latest iteration of room temperature electronics. We can now, in the same footprint, control and read out 80 times more qubits than this commercial off-the-shelf electronics could do, and for a lot smaller price tag. So we're extremely excited about that. And of course, we keep on working on pushing that even further. Second, like I said, what we need to do is we need to get these signals in and out of the chip. How we do that? Back in the day, in that fridge, you would see coaxial cables. These were the vertical metallic lines that were running inside the fridge. Here we have a close-up image on the left of that. It's a further iteration of that. It's our past high-density coaxial wiring example. But in our present setups, what we turn to is cryogenic flexible wiring. What that is, it's this cardboard-like sheet that packs a lot more signals, 70% higher density of signals than the coaxial wiring, and it helps us actually reduce the number of connectors and components that we need to connect to wire up the devices. So that limits the number of things that can also go wrong. It's a great way to take out engineering risk from the setup. Furthermore, it reduces cost in our systems, and over the next year or so, we aim to increase the density of wiring by another factor of 3 or so. Moving on, 10 years ago, what we had in that photograph was a chip that we basically put into a PCB, and then the way we connected it to the PCB was we wire bonded from the PCB onto the chip. Now, that works fine as long as the topology of your quantum computer is either a line or a ring. But unfortunately, this is not how we want to build a quantum computer. So we had to move on from that. Moving away from the single layer of metal wire bonded to the PCB in the previous slide, that was our first generation of packaging technology. We then turned to flip chip technology that you can see in this slide. That technology now uses 2 different chips that have 2 distinct roles. We have a qubit chip and an interposer chip. The interposer chip has a role of routing signals to the qubit locations, and we also use it for placing readout resonators near the qubit chip. The 2 chips are bonded together using superconducting bump bonds, which are there in the image wedged between the 2 chips. And the interposer chip is connected to the outside world, which is the PCB, using wire bonds, which are these wires that come in from the sides. This technology was used, for example, in our Hummingbird processor. Now, this helps us a little bit because it gets us to nearest neighbor coupling architecture. It doesn't constrain us to only linear or ring topologies, so that's great. But it has some drawbacks. For example, when we route the signals on the interposer chip, then the metal layers there are not shielded, which means that when we go past the qubit, we can inadvertently have crosstalk to qubits that we don't want to have crosstalk to. Moreover, we have only finite real estate there on the periphery, and we would like to increase the amount of signals that we can get in and out of that interposed, for which we have to turn to our generation 3 packaging technology. So here what you see is multi-level wiring technology. What we've done is we've still kept 2 different chips, still the qubit chip, where we fabricate our qubits. We still have the interposer, but at the bottom of the interposer, we have multiple layers of metal and dielectric that are insulating metal layers from one another and effectively forming a strip line, transmission lines there at the back of that interposer chip. And that enables us to route signals to the qubit site in a shielded manner. Now, when you go past qubits on a qubit chip that you didn't want to target, you know that your signal is not cross-talking to them. The way we get to the qubit site is using these through substrate vias that you can see here marked with brown in this figure. So there are really two elements of the technology that we've introduced, the TSVs and the multi-level wiring, that are critical for us to scale everything up. So going further, what we've done is we've been able to extend the multi-level wiring to 5 layers of superconducting metal, which means that we can even cross these transmission lines at the back of that interposer wafer with one another. So this gives us plenty of opportunity to route to any location on the qubit chip. And it also frees up a lot of space on the qubit chip that we otherwise had to use for wiring and other purposes that were undesired. So going from Osprey to Condor processor, for example, even though the qubit count increased by 2.5x, the space that we needed for the qubit chip actually only increased by 1.7x because we had this technology. So here I just show you, to repeat what I've already been saying, in a 3-dimensional structure for our packaging. We have this MLW multi-layer wiring and through substrate via technologies that helps us tremendously for scaling up the architecture. We have a qubit plane where we lay out qubits only. We have a readout plane where we have the readout resonators. These two are bonded together using superconducting bump bonds. Then underneath the readout plane, we have the wiring plane that is connected to the readout plane with through substrate vias. And all of this leverages CMOS packaging techniques to bring these together. We couldn't have done it without borrowing very, very heavily from CMOS technology, which we have at IBM in the house. Now, I've told you about everything apart from the chip itself, the qubit themselves. Of course, we also need to work on the qubits and the chip too. And here in this plot, I want to show you the evolution of our devices, both in size. We started off here with Falcon-sized devices that had 27 qubits, moving on to Hummingbird, then to Eagle, 127 qubits, then to Heron R1, 133 qubits, Heron R2, 156 qubits here on the right. You can see that over the past 7 years or so, we've cut down the qubit error rates by an order of magnitude. And here our best gates for Heron devices now reach below 10 to the minus 3 error rates. That is, we've both increased the processor size, but we've not had to sacrifice on the error rate. Quite the opposite. We've actually been improving on both of these fronts. Moreover, Heron introduced tunable coupler architecture, and compared to Eagle, which did not have that architecture, Heron also reduced crosstalk. So here we're looking at a simple experiment where if you apply a pi-half pulse or a Hadamard gate on neighboring qubits and see just the free evolution of them, what happens on an Eagle processor when you do that simultaneously on these qubits and you do that in an isolated manner, what you can see is that doing that in an isolated manner, then you don't observe really any decay over 20 or so microsecond evolution time. Whereas if you do that operation as a multi-qubit operation, you start observing a decay over 20 microseconds. If you turn to Heron, these curves look effectively identical. Heron's architecture with tunable couplers basically takes out crosstalk at timescales here up to 20 microseconds. So going through some Heron facts, what we now build are processors with 156 qubits. The qubits themselves are fixed frequency transmons. The couplers between them are tunable, so that enables us to run fast gates. You can see that from Eagle to Heron, the gate times have gone down 5 to 6 times. That also means that the gate errors have gone down significantly, and crosstalk is much reduced for Heron processors. We've kept the same heavy hex lattice connectivity for now, and we use the same multi-layer wiring for Eagles and Herons alike. Again, comparing the performance of best Eagle processor with the first Heron processor here. This is a Heron R1 processor. You can see that the Eagle, when operating gates in a layered fashion, has significantly higher error rates than operating them in an isolated fashion. Whereas for a Heron processor, these curves are rather similar. So that again is a testament to Heron reducing crosstalk significantly and its gates being much more robust to being run in a layered structure. And by layered, I mean running them in a simultaneous manner. Okay. Now, I want to move forward by telling you a little bit about the future. And for that, I want to take a look at our roadmap. So our roadmap is broken apart into the development roadmap and innovation roadmap. And what you can see is that in the innovation roadmap, we have a lot more different bird names than we have in our development roadmap. And the reason for that is that in the innovation roadmap, each bird has a specific purpose. It's meant to develop a specific technology that we want to bring to life, that we will need either for something that will give us a pathway for quantum advantage or for further down the road error correcting quantum computer. So going forward from here, I want to focus on the innovation roadmap and really 3 birds here, flamingo, crossbill, and kookaburra, and the technologies that they all develop on our path to error correcting superconducting quantum computers. And these technologies will be brought together in Starling and then further down the road, Blue Jay, that will be much bigger birds with a lot more qubits. So first, before I tell you about these technologies, I will tell you about the error correcting code that we want to implement with the technologies that we're building. So in this paper, from last year, what our team showed was a family of codes, quantum error correcting codes, that significantly reduced the overhead needed in the qubit count for reaching the same kind of thresholds that the sort of darling of the error correcting community, surface code, had previously shown to reach. But the qubit count was 90% lower. So you can see the code that was dubbed gross code used up 144 physical qubits as compared to the surface code's roughly 1400 to reach the same distance and the same number of logical qubits to reach the same logical error rate. And that's really significant, because if we can reduce the qubit count by that much, then that makes building these devices a lot easier. Now, of course, there is a catch here. The catch is, for implementing these codes, what you need is long-range couplings. The property of surface code, and the reason why people like it, is it has only nearest neighbor couplings, whereas this gross code, or more generally what the authors have since then developed, these bicycle or bivariate bicycle codes, need long-range couplings between qubits. It could be seen as a technical hurdle, but of course, superconducting qubits are electrical circuits, and there's no immediate technical limitation that says that the couplings there have to be nearest neighbor. And I'm actually going to try to convince you with the rest of this presentation that this is exactly what we're going to embark on when trying to build the hardware for it. But at first sight, the task might be a bit daunting, because what we need to do is we need to go from our current architecture, which is this connectivity graph of heavy hex on the left that you can see, which is used on Heron processors currently, to something like that you can see on the right. And the reason why it looks like such a mess is because now we've introduced this 6-way connectivity, and that means that you cannot lay it down on a surface anymore. We need to break the plane with our couplings. So what you see here is these coupling elements snaking around between various lattice sites. But our efforts are underway, and we're taking it step by step. There are 4 specific efforts that I will tell you about that we're currently working on towards implementing these codes. And the first one of them is we just want to show that we can do 6-way connected nodes of our qubits. And for that, we don't yet want to demonstrate long-distance couplings, and we will not demonstrate that in breaking the plane configuration, but we just want to show that this works without degradation of coherence, and we can still maintain good error rates for gates. Second effort that we have in parallel with the first one is demonstrating that we can physically realize these long-range couplers, that we can route a connection between a qubit on one side of the chip to far away, and do a good gate between them. Third effort that we have going on is that we can cross couplers that we call C couplers. The C coupler is a terminology that we use for couplers that are on the same chip. We want to show that we can actually go and cross them with one another, again without degradation to performance. This is a critical aspect for these codes. This is an enabler of beyond 2D connectivity. And last, because these codes get so complicated, you cannot really imagine anyone designing these by hand. We need to develop automation tools for designing these circuits. So we want to also develop design workflows and processes that leverage existing CMOS design techniques and therefore iterate our design processes more rapidly. All of these efforts are going on in parallel, and I'll show you examples of that. First, increasing connectivity. So here, as mentioned, is our first device that consists of 7 qubits, 1 in the middle, 6 surrounding it. They're labeled by Q0 to 6. And in between each of these nodes are tunable couplers labeled by TC in this figure. You can see their coherence times, we give them here. And with this device, it was fabricated in a single plane. And these tunable couplers, they're not long range. But what we wanted to see was whether we take a significant hit in coherence times when we engineer this 6-way connectivity, which isn't really the case. We can still maintain coherencies of order 100 microsecond or even higher. And we wanted to see what kind of gate fidelities we can achieve. So in purple in this slide, I give the 2-qubit gate fidelity, gate error rates that we achieved when realizing 2-qubit entangling gates between these qubit pairs. So you can see all these gates had error rates ranging from 3 e to the minus 3 to 5 e to the minus 3. So it's kind of similar to Heron error rates. So this is very encouraging. It shows that we can fabricate devices like that, and we can keep crosstalk down while performing gates on each one of these pairs. Moving onwards, like I said, the next challenge for realizing one of these error-correcting codes is realizing long-range couplers. On the chip, we want to be able to perform 2-qubit gates between qubits that can have any distance between them. So what we've been doing here is, again, on a single layer, we've been trying out different distances and couplers of different distances between qubit pairs. So again, we have tunable couplers, and lengths range from 6 millimeters to 18 millimeters. The 18 millimeters being really long, and seeing what kind of gate errors do we achieve when we stretch our couplers out that far. Now, the challenge when you do that is, can you get significant amount of coupling between the qubits? And that will translate to gate fidelities, because if you can't get enough coupling strength, then within your coherence times, you will see a degradation of your gate errors. But as you can see, the gate errors here are really good. They're actually even better than median gate error rates for the Heron processor that I was talking about earlier on. Now, trying to put all this to work in a real device, taking these components, what we need to do is we need to take the existing architecture that I told you about earlier on, where we have the qubit plane, and what we need to do is we need to extend the qubit plane, and we need to replicate something akin to the multi-layer wiring that we have on the interposed chip, also on the qubit chip now on the back side here, What we need is these low-loss interconnects between non-neighboring qubits. And this is exactly what we've been working on. And they also have to be shielded for the very same reason that I was talking about earlier on. So we have our first test device that we've measured, where we actually built one of these structures, and we didn't constrain ourselves to be just in a single plane like for the devices that I went through up until now. Here, what we're doing is we are crossing over different levels, and the example of a gate that does that is here given by the red tunable coupler in this figure. And again, in purple, I give the 2-qubit error rate that we've achieved with such a structure and the respective coherence times for the qubits. You can see the coherence times similar to what they were before. The tunable coupler that basically bridged, that broke the plane, gave a good 2-qubit gate, 3⁻⁻3, similar to the black one here that was run on the same plane as the qubits line. So we've shown that there's no real degradation that our gates suffer from breaking the plane. Finally, we don't only want to lend CMOS tools for fabricating our chips. We also want to leverage as many existing CMOS tools for designing them. So here what we do is we try to use as much existing CMOS interchange formats, for example, open access format for electronic design automation. In this flow diagram on the left, what I lay out is our current workflow for designing the chips for these error correcting architectures. What you might recognize if you've ever been exposed to CMOS or maybe even PCB design is these routines seem very similar to design workflows in these processes. And that's exactly what we do. We try to leverage that. We design our components, and then we tune them with software, but the routines where existing tools exist, we try to make use of that. And an example output of a chip would be there on the right. You can see it's this colorful mess of lines. And that's exactly the point. At this stage, our chips are getting so complicated that no human could feasibly design them, and we have to rely on computers, just like for processors for classical computers. So as the last topic, I want to touch on how do we build even bigger quantum computers that consist of multiple chips. So far, we've been talking about hardware that is needed for building devices that effectively consist of a single chip. And for that, we were talking about these C couplers, and they were long distance, but they were still routing between a qubit site on the same chip with a different qubit site. But inevitably, we will need, because of size and other considerations, we will need ways of coupling together multiple different qubit chips. And what we use for doing that are two different couplers. We will use M couplers and L couplers. And like I said, on our roadmap, on our innovation roadmap, we have two different kinds of birds, flamingo and crossbill, that are intended to tackle exactly these purposes. Flamingo will attack L couplers, which are long-range couplers between different sets of chips. They're here drawn between these sets. And crossbill is tackling couplers that connect chips that are set next to one another. So here's an example of a test device that implements technology that goes into cross-build. So it's a chip-to-chip gate, 2 chips lying next to one another, and there's a tunable coupler between them. You can see there's a chip boundary, and we managed to implement the gate with a 1.5 e to the minus 3 error rate for an entangling gate between these 2 chips. And you can see the coherences of the qubits are, again, respectable. So cross-build device will have, or has, 3 of these chips next to one another, and on 2 of these interfaces that you see in this figure, there are M couplers connecting the qubits between the chips to one another. It also features high-density connectors that you can see in this figure and large-scale silicon packaging. However, if there are further size constraints, we can't put all chips into the same package quite like with cross-build. We will need to connect the chips with effectively coaxial cables or some other superconducting link. And for that, we need to use what we call L couplers. And this is a technology that we've been developing. And here is a result that was published in the paper cited below. We managed to get a 2-qubit error rate of 6.7 e to the minus 2 for 2 qubits connected by a link that is 60 centimeters long, 0.6 meters. Well, this is really long now. Compare that to the C couplers that the longest that I showed you before was 18 millimeters. So the 60 centimeters really lets you wire them inside the fridge with some flexibility. The technology here comes with added complexity. What you need is 2 tunable couplers plus these tunable coupling qubits. And as you can see, the error rate's currently somewhat higher than what we've seen for all the other error rates that I've shown you today, but we're working on improving that too. So this is the technology that forms the basis of Flamingo. Flamingo here is a Flamingo that connects 2 packages with 4 L coupler connections. Each of them is 70 centimeters to 1 meter long. These devices moving from the innovation roadmap to a development roadmap this year. To summarize, we've walked through 10 years of engineering progress in control electronics, wiring, packaging, and no less importantly, quantum chip performance. And then we look to the future and our plan for engineering towards error-corrected superconducting quantum computers and the elements necessary for that, including long-range on-chip couplers, new design tools, and multi-chip technology. Thank you very much.